With that, we're going to jump into our next presenter, which is Marina Zhang, who is a licensed professional engineer with 18 years of experience in transportation. As a field engineer with Bombardier Transportation, she was part of the teams that built the Vancouver SkyTrain Millennium Line and the New York JFK International Airport AirTrain. Now, as a senior research engineer at the National Research Council Canada's Automotive and Surface Transportation Research Centre, she is leading sustainable and climate resilient surface transportation research. Please join me in welcoming Marina.
Okay, thank you very much. I'm trying to share screen. It says I cannot.
You can. It looks like your screen's already shared on my end. Are you looking at the?
Nope. That's.
Oh, maybe Ted, can you stop sharing?
Is that my screen? I don't think it's my screen.
It might be. Ted might have to stop sharing before you're able to. How about now?
Okay, let me give this a try. Okay, can you see my screen okay?
Yeah, looks good on my end.
Okay. I'm just gonna get ready for. Okay, so thank you very much. My co-author Ali and I would like to thank the organizers of this conference for the opportunity to present today. I am going to move straight on to the presentation itself. So the Canadian Rail Network traverses some of the harshest climatic zones in the world. And in fact, temperatures in Canada have registered from minus 63 degrees Celsius, which was recorded in Snag, Yukon in 1947. And I know that's not really close to where tracks are laid, but of course, we've also seen the other extreme where temperatures have soared to 49.6 degrees Celsius, which was recorded, in fact, this past summer in Lytton, British Columbia. And that's right along a key rail corridor. Since there are no gaps to allow for thermal expansion or contraction, large thermal stresses can build up in continuous welded rail, or CWR, when it is subjected to temperature fluctuations and extremes, which could potentially lead to failure. Because CWR is preferred for mainline track, this makes rail one of the most vulnerable modes of transportation. So in the context of climatic changes in Canada. So speaking of climate, let's take a look at climate in Canada. So we know that climate in Canada is warming. Anecdotally, I'm sure that most people remember much colder winters when we were younger than what we've been seeing the last few years. Looking at the hard data, we know that between 1948 and 2016, Canada as a whole, we've experienced an increase of 1.7 degrees Celsius, and that is the average temperature. It doesn't sound high, but we are talking about, across Canada average. And so that the extremes do compensate for each other. So we see that our rate of change in the blue line compared to the rest of the world, we're at roughly double the world average. And we know that some parts of Canada has experienced much more rapid change. For example, our Arctic, which is shown in the gray, it's almost 3 times the global average. And as well, we've seen across Canada a decrease of more than 15 days, frost days. These are referring to days where the daily minimum temperature is less than or equal to 0 degrees, and more than 10 ice days, which the daily maximum temperature is less than or equal to 0 degrees. And we've also, on the other hand, seen an increase of extremely hot days. And this, going into the future, it's expected that this warming trend will continue in every region across the country. And so the objective of this presentation and paper is to provide information really on how these projected climatic changes will impact CWR. We want to introduce climate models and data and ways we can incorporate future climate scenarios into the way we manage thermal stress for CWR. We'll look at a case study as well as some recommendations in terms of the next steps. So what are the potential implications for CWR? What we know is that we're going to start seeing larger and larger compressive stresses from warmer weather than we have seen in the past. There is going to be more needs for inspection due to warm weather extremes. There are going to be more needs for hot weather slow orders. There's going to be a lot more needs for rail distressing. And, in the near future, there will come a day where there's going to be a need to start reviewing the rail neutral temperature values that we use currently, especially in regions that's undergoing more rapid warming. And I'm sure that I'm not telling anyone what they haven't already experienced in the field. What I really hope to do is to provide the hard data to confirm the observation, but also some tools to help better planning and to mitigate for these changes that are actually already underway, but are going to potentially get a lot more severe. And so one of the tools that I would like to discuss is climate modeling. And so I'm sure that we've all heard of terms like climate models, climate projections, climate summit. We hear them pretty regularly. And it's, even though it is a familiar term, I certainly didn't know much about it until I actually started to use it. So what are climate models? Essentially, they are composed of mathematical models that describe a lot of the physical and biogeochemical processes that happens on Earth. So they're also referred to as Earth systems models. And together they almost create a virtual planet. And so they examine things related to climate, such as the interactions between the atmosphere, the ocean, the land surface, the cryosphere. So they are pretty complex. And these models simulate historical climate. So what happened in the past. They also make projections of future climate based on the expected human activities, we also call them emission scenarios. So these processes happen at a global scale, so they don't have any geopolitical boundaries, and generally they are done at a very large resolution, sometimes 100 kilometers or more. So what is very important to note is that all climate models have uncertainties because the mathematical processes for these are approximated. And so usually what we do is use an ensemble of different models so that they compensate for each other's uncertainties, but they also produce a range of expected results. So what ensemble should one use? Well, the Coupled Model Intercomparison Project, or CMIP, which is established by the World Climate Research Program. They've been the gold standard for climate models. So the climate models developed within this project follows a set of standards and protocols. And so the climate models and projections developed within the 5th phase of the project, CMIP 5, are the ones used in the Intergovernmental Panel on Climate Change's 5th assessment report, which was released in 2014. So that is the current gold standard, but the development of the next phase is underway. And so is expected to contribute to the next IPCC assessment report, which is expected to be released within the next year or two. So this is a very brief crash course on climate models and data. Like a brief recap is they consist of Earth systems models. They have uncertainties, use an ensemble, and the CMIP5 is the current gold standard. So what does it mean and how do we relate it to CWR? So what we know is that thermostress buildup in CWR is pretty complex. And there are many factors at play, including the rail neutral temperature, the rail temperature, track resistance. These are all parameters that are pretty hard to measure. It's not impossible, but to measure them is time consuming, it's costly, and in order to do it system-wide frequently is definitely a major challenge. So one of the parameters, the rail temperature, even though we know that rail temperature can be impacted by factors like sun exposure, wind conditions, and shade and topography, we also know that it is strongly influenced just by the ambient temperature conditions around us. And this is a parameter that is measured and is recorded across Canada and much more readily available. So I show in this schematic, the weather stations are in these red dots and the rail network is in yellow, just to see that even though it's not uniformly distributed, but there are a lot of weather stations across Canada. So the proposed method makes use of data that's readily or more readily available in the public domain. So what is the approach? So as I mentioned before, very briefly. And I'll describe it through this schematic here so that climate models have a historical portion and a future projections portion. And so in this example, the historical portion is from 1963 to 2012. So what we can actually do is we can take the historical portion that's simulated by the climate model and compare it with the actual weather station observations to see how good it is and whether we need to develop a calibration function. And if so, we would take the calibration function and integrate it into the future projections portion of the data set and produce a calibrated data set. And usually this calibrated data set would be available in the form of monthly average temperatures. Then we would use one of the many downscaling methods to produce daily data sets. And it's the daily data sets that we would use in terms of generating scenarios into the planning process. So I know that sounds very theoretical. So I wanted to, present some of the example data and analysis in a case study, just to maybe illustrate how useful using future climate model data can be. So Kamloops, British Columbia was selected in this case as a case study because we have continuous records from 1951. It is situated near a key rail corridor. The whole region experienced record heat during the summer of 2021. And also the number of annual hot days for the region is projected to increase under all future emission scenarios. So here we have the data from the Kamloops weather station, and that's shown in these black dots. And then we also have data from a 24 climate model ensemble from CMIP5. And so the simulated historical portion is from 1950 to 2005, and you see that in the black lines here. And the projected future is from 2006 to 2100 in these colorful lines, and the color depends on the emission scenario. So what is actually also very interesting is that obviously from 2006 to 2021, today, we have actual weather station data. So we can use that and look at how good the projections are. And so some of the example analysis we have to show is that we can take a look at the coldest temperature and the hottest temperature, so the extremes. And so what we see here is with regards to the coldest temperature, with some exceptions, some years have registered much colder temperature than what's projected. But in general, without calibration, the region had experienced much warmer winters than what has been projected. And in fact, if there's no calibration done on this data set, it looks like, in fact, it is on track to the highest emission scenario. And along the same trend, the region has registered much warmer summers than what has been projected, again, with some exceptions, and again, on track to the highest emission scenario. Some other types of data and analysis we can take a look at is how many days within a year are we expecting, or have we recorded or expecting extremely cold? So days minus 25 or below, and extreme hot days where they're going above 30. And so what we see is that the region for many years, even dating back as early as the 1950s, there's been many years where there has been 0 days, extremely cold days. And again, there are exceptions, but generally we don't see more than 6 extremely cold days. And that trend is expected to continue under all future projections. Regardless of emission scenarios, we're going to see less and less extremely cold days going into the future. But on the flip side, the region have recorded much, much warmer summers. In fact, even as early as the 1950s, there's been at least 1 year where the number of hot days above 30, it's almost 2 months or more than 2 months of days above 30, and again, on track to the highest emission scenario. So that's a very brief presentation of the paper, but in summary, without expansion gaps, CWR is vulnerable to temperature fluctuations and extremes. We explored how projected climatic changes will impact CWR, and some high-level information on the tools and a method to be able to start incorporating future climate scenarios into the way we manage thermal stress from these climatic changes, as well as a case study on Kamloops. So, recommendations to the future. We know that climate in Canada is changing. However, the rate of change is not uniform across Canada. Some locations along the rail network will be more vulnerable than others. So it is important to determine which locations are most vulnerable to climatic changes. We can look at rates of warming, projected extremes, projected annual numbers of cold and hot days. And of course, I'm also interested in from those in the audience, what other types of information will be valuable for CWR thermal stress management. We should also start looking at past climate records, the RNT used, maintenance records, and operating speed records to determine what degree climatic changes have already impacted CWR. And then to start using the latest climate data to determine is there a need we need to start refining construction, operation, maintenance methods within the next few years, 5, 10, 15. And so that's pretty much it. I'd like to thank my silent partner on my co-author on this project, as well as Crown Indigenous Relations and Northern Affairs Canada for supporting climate resilient transportation research, and our colleagues at the National Research Council. So back to Kevin.